Are you the type of person that sees this image and can tell where it is? Well, don't worry about it, it also happens to me. That's why in this video, I will be showing you how to create an AI to help label images of transports and animals. If it's your first time, don't worry. I've adapted the tutorial to people like me who has zero knowledge about AI, neural networks, datasets. Well, let's get into it. For this tutorial I've chosen Python as the programming language because it offers libraries which tend to make the process a lot easier compared to doing it with other languages like C++ or maybe Java. Python offers some nice libraries for AI. TensorFlow is an example of it, but we also have Keras or PyTorch. And we will be using also NumPy for managing the data and Matplotlib to visualize or show an example of the images we will be using to train the AI. The first thing to start the project is to install the libraries. We can do so with the command of pip install, or if you're using an IDE like PyCharm, you can go to Python packages in the left down corner and install them manually by typing their names inside the search bar. Before jumping into the code, let's quickly cover two key concepts: datasets and neural networks. A dataset is simply a collection of data used to train AI models. We will be using CIFAR-10, which contains 60,000 small images across 10 categories like dogs, cats, and cars. And a neural network is a model inspired by the brain, made up of layers of neurons that process data. Input flows through the network, gets processed in hidden layers, and produces an output like a prediction or classification. We'll train a neural network to classify CIFAR-10 images by adjusting its internal connections during training. With this clear, let's dive into the code. Now, for the code, we will start by importing the necessary libraries for the training of our model. For this task, the only lib needed is Keras, which is actually built inside TensorFlow. Keras is just another AI library focused on neural networks. As you can see, I imported layers and models, which are essentially for the AI, but also the dataset by itself, and a utility we will discuss later. One of the best things of Keras is that it has some datasets built in, so we don't need to download it manually. They are automatically downloaded into variables when we specify so, which is what I'm doing right now. As you can see, I am declaring two tuples, one with x and y train, and another with x and y test. Here, x and y don't mean actual coordinates, but parts from the dataset. X being the images and Y being the labels or names. When we split the dataset into training and testing sets, each one has a specific purpose. Training data is used to teach the model, and it contains the input features, which are the images in this case, and their corresponding labels. These labels act as the answers the model learns to predict. The training process involves adjusting the model's internal parameters to minimize errors in prediction. The testing data evaluates how well the model generalizes to unseen data. This part of the dataset has the same structure as the training data, but consists of examples the model has never encountered during training. By using this data, we can measure the model's performance and identify if it's overfitting, which actually means memorizing the training data instead of generalizing patterns. For example, if the model achieves high accuracy on the training data but performs poorly on the testing data, it means the model isn't generalizing well. This testing process simulates real-world scenarios where the model encounters new inputs. Now we're going to normalize the data, which essentially means adjusting the values in the dataset to fall within a specific range. Each image in the dataset contains three channels: red, green, and blue. And each channel has a pixel values ranging from 0 to 255. These values are relatively large, and when the neural networks process them, the large difference between values can cause instability or slow down the training process. To address this, we normalize the pixel values by scaling them down from a range of 0 to 255 to a range of 0 to 1. This makes the data more manageable for the neural network while preserving the color information. We have seen the tweaks for the images, but what about the labels? The labels are essentially strings of text containing words. These words contain characters with their proper encoding and everything. If we feed those strings to another network, it will have to process all the characters and words lengths, making the process very hard and unstable. As I mentioned earlier, we imported an utility which is called toCategorical. This function simply assigns each label a number. For example, airplane is now 0 and deer 4. This process is called encoding. This encoding makes the AI only need to memorize numbers from 1 to 10 instead of all the characters in the labels. Now we have all our data processed, we can start building the actual network. For it, we have to assign to a variable the model function. Sequential means that the networks will be stacked one after another. This is the best type of network for images. Now we'll need to pass as an argument an array containing all our layers. The first layer we are going to pass is the input layer as a convolutional layer. The input layer has a matrix of 32 by 32 neurons, which are the size of the image resolution, as well as 3 channels, which will represent our 3 colors we talked earlier. Convolutional works best because it makes each layer have filters that slide over the image, recognizing patterns such as edges, textures, or shapes. Also, we will put a max pooling layer there to shrink the image while keeping most important information, to help the network work faster and prevent it from focusing too much on tiny details that might not matter. Then we will add another convolutional layer with 64 filters and finally another one with 128. After adding our 3 convolutional layers, we will need to unroll the grid-like format of neurons that our convolutional layers had to a flattened format, which will put the neurons into a single list of numbers. This is necessary because the next part of the network, which are fewly connected layers, expects inputs in a flat format, like normal arrays in programming instead of a matrix. The dense layer, after flattening the network, has 128 units and it processes the flattened data to learn at a higher level combination of patterns. It acts like the decision-making part of the network, where it combines all the features it has detected so far. And finally, our output layer, which only has 10 units, one for each category on the CIFAR-10 dataset, and the softmax activation function will convert the network output into probabilities for each category. It's like how sure the network is that the images is the category it says. After building our network, we have to train it with the actual data. For it, we will use the item optimizer, which simply helps the network learn efficiently. Then categorical cross-entropy loss, which measures how far the model predictions are from the current labels. And also we will ask the training function to keep track of how many predictions the network gets right. After training the model, we'll have to save it to a file so we can use it later. Now let's run the code and see the magic happen. At first, we see a couple of warnings that TensorFlow gives us. That's no problem at all. Then we start to see a message that says epoch. I forgot to mention it earlier, but an epoch is a full pass through the entire training dataset by the neural network during training. Essentially, it means the model has seen and processed every training example once. There is not a specific number for epochs, but there is always a sweet spot, which is essentially a range between numbers. I found that with this neural architecture, 20 is a sweet spot. Any number higher will improve the accuracy by a small margin, but at the cost of increased training time and the risk of overfitting. This diminishing return means that while the model's accuracy might slightly improve, after 20 epochs, the improvement is often not significant enough to justify the extra computational effort. By stopping at this sweet spot, you balance performance and efficiency. However, always keep in mind that the sweet spot can vary depending on factors like dataset size, model complexity, and the optimization strategy. While we wait, we can see the accuracy percentage goes up on each iteration. And after finishing all the epochs, after the final one, we can appreciate the number of accuracy the model received from the training data. In my case, I got a 20% accuracy, which is pretty great. Now if you look at the script directory, a new file should have popped up. And you should now be asking, how are we going to use the model? Well, we need to code a new script, but don't worry, this one is much simpler. For this new script, we are going to import TensorFlow again as TF, then NumPy, TensorFlow preprocessing, and Matplotlib. For visualizing the image, we are going to feed the AI to. First, we load the model with Keras models load data. Then create an array with the CIFAR-10 labels. But why this? Well, remember the two categorical function that converted labels to numbers? Well, now we are doing the reverse with it. To keep the code simple, we are going to make a function and we are going to pass it our image directory. Then we are going to load it and resize it to 32 by 32 pixels. After which we are going to normalize it like we did before training the network. This is because the AI is not prepared to see images that have different processing or format than the images it has been trained with. Don't worry, this is not cheating. It happens even in the largest AI and language models. There is always some kind of processing under the hood. After it, we are going to convert the image into a 3-dimensional matrix that has the 32 by 32 pixels and the 3-color information. And finally, predict it with model.predict. We can print the result if we are curious. But we need to get a predicted class label because the model.predict function outputs all the labels probabilities instead of just the correct answer. So we are going to get the highest number of all the predictions. To keep the script clean, we can show the images as well as the prediction with matplotlib and return the label that was predicted. Finally, specify the image path and predict. As you can see, I have prepared 4 different images to test the AI. If you look at the file type, they are not the same format, but thanks to the script we made, that's no problem at all. Now, to predict, first we need to specify the file location. And then hit run. A new window should pop up with the image we input. But it looks different, doesn't it? That's because we are now seeing the image the actual AI is seeing, instead of the normal one. Also, if you haven't noticed by now, the prediction is on top of the image. But if we now look at the terminal output, we can see an array containing numbers from 0 to 1. These numbers are the probabilities we mentioned earlier. As you can see, the highest number has the same index as the horse in our class names array. Now let's try with the other images. The plane, which appears to be the most complex one, was predicted successfully, and then the truck and the frog too. This means that the AI is working perfectly. I hope this video made you understand a bit more what's behind artificial intelligence and the tricks they do to actually work. Please consider liking the video and comment what you want to see next. As always, if you have any problem or question, leave it in the comment section, and I will try to help you as soon as possible. Thanks for watching and happy coding!